Well, hello everyone. This is KP the Math G here, and it's a delight to be able to help you with some more calculus. I love this. This is the big three in AP Calculus, and I'll tell you why I started off with that. When I went to workshops, all we could talk about at the beginning, especially if you were a beginning calculus teacher, were the big three. And even after we got even more advanced, they still emphasized the big three. And the big three are limit, derivative, and the definite or indefinite integral. And so if you can kind of get that, of course there's a whole lot of concepts built into all three of these big three, but that's why they're called the big three. So what we've been doing is that I believe I have 6 videos so far on the big three. We've already talked about limit. We've done a lesson or two on derivatives, I think maybe 3 lessons. And so what we want to do is we want to continue on answering this question: when do I use a derivative? Because when you take that test, well, you need to look at the problem and say, okay, do I need to take a derivative, or do I need to integrate? In some cases, you might want to ask, do I need to take the limit? Okay, so yeah, if it appears that my hair is just all messed up, I can't tell whether it's messed up or not, but be that as it may, I've been outside and it's been hot, and I've been working out at the gym. Come home and do a little something outside with my dogs, and I'm sweaty, so I'm going to be going out to drive a bus pretty soon, so I'm just in my kind of my bus clothes, so bear with me today. Alright, let's get started here. When do I use a derivative? Well, one time we talked about using a derivative is when we wanted to find out if a function is increasing or decreasing. You can actually take f at x or g at x, and just without drawing the graph, you can tell whether that graph or the function of that graph is increasing or decreasing. Isn't that something? Just by finding the derivative. Which means that you can also use the derivative, and then actually in doing that you're finding the slope. And you can look at the slope of a tangent line, the slope of a normal line, which is perpendicular to the tangent line, and so on. So all sorts of concepts built into that. And then I'll tell you what we're going to do. We're going to do one where you find the velocity. So, and acceleration for that matter. I don't know if I did anything to do acceleration. I don't believe I have. Okay, so let's talk a little bit about doing that. Okay, so let's start with, and so what we're dealing with here is uniform motion. And let me move. I'm standing behind a bed is what I'm doing. And okay, and that was anyway. All right, let's go ahead and start here. Okay, here is what we call a position function. S at t. A lot of times it'll say x at t, maybe, is a position function. Okay, and this is equal to negative 16 t squared plus 16t plus 32. I want to say it's everything's positive, negative 16. What this is, if you look at this very carefully, it is a graph of kind of like a parabola, and you'll know that I'm kind of going into some trivial things about this. But at any rate, this negative in front of the t squared just simply means that the if this represents a ball being thrown up in the air, it is going to be curved downward. Okay. All right. You're going to have a vertex up high. If this is positive, you'll have a vertex down low. But that's beside the point. Just kind of recognize things like that when you're dealing with a problem. This is actually a position where like a particle is rolling along either an x-axis or a y-axis, or sometimes even both, and it is represented by this equation. Position equation is what we call it. So what we want to do is we want the velocity of this. Using this, we can find the velocity. So here's how we do it. S prime at t is equal to v at t. That's your velocity right there. Now we're talking about a rate of change. Speed. Actually, it's the absolute value of speed is going to give you your velocity. Actually, absolute value of velocity rather than speed. Speed is never negative, but velocity can be either positive or negative. Okay, so kind of keep that, but still the units are the same: feet per second, miles per hour, centimeters per second, or something like that. So alright, this is going to be v at t. We're taking the derivative. We know how to take the derivative of a power function. So negative 16 times 2 is negative 32 t. And then, remember this is a 1 here. 16 times 1 is 16. And remember this becomes a 0. And it's t to the 0, which is 1. But 16 times 1 is just 16. Derivative of a constant is just 0. So that's the velocity of this. Okay. If you want to look at this after 1 second, alright, so S prime at 1 is actually, you just really want to do V at 1, and then you just plug in the second right there. After 1 second, the velocity is, alright, so this is negative 32 plus 16, and that's a negative 16. If this was in feet per second, you're going to write this in feet per second. Incidentally, this is going to be in feet if you're talking about feet. Or it could be miles, it could be centimeters, a unit of measure like that. You change, or you're converting it to feet per second in this particular case. Alright. This means that the particle is moving left. If it were positive, the particle is moving right. Okay? So I don't know if I could back up 16 feet per second. I'm not so sure I can even run 16 feet per second, let alone back up 16 feet per second. But that's what this is. And so this is moving to the left. You don't say, if you say left, you're already saying negative. So don't say negative 16. You're saying the particle is moving left 16 feet per second. Okay? At a rate of 16 at t equals 1. Okay, that's what we're doing. Okay? Alright, and I'll assume that we're saying that the units are in feet. Well, that the time is in seconds. Okay? Alright, now I'm going to do one more thing here. Oh, well, I was dealing with just first derivative. This is a first derivative. So the first derivative is all we're talking about right now. If we had to do a second derivative, which would be easy to do, we can do a second derivative on this, and what we would find from velocity is acceleration. So you start off with s at t, that's the position function. Where is it? Where is it on the, say, x-axis at t equals 1? You just simply plug in 1 and you'd figure out where it is. And actually, if you plugged in 1, you would get 32. So it would be 32, if we're talking about feet, it's 32 feet from the origin, or from where it starts. Okay, so it has a starting place of 32 feet. Okay. All right. If it's the y-axis, it could be way up 32 feet and you're getting ready to drop the ball. Okay. But anyway, there it is. So s prime at t is your first derivative. So the first derivative is s prime at t, which is v at t. And then your second derivative is going to be v prime. Actually, we can say this. It's the second derivative s double prime at t, which is v prime at t, which is a at t. Right there. So actually, you're moving from position to feet per second, and in this case we would have feet per second, which is feet per second squared. Okay, and that's how you would do, and we'll get into the second derivative. When do you use a second derivative? Later. Although I did kind of introduce the second derivative to you and say, okay, you want to get to position, and you say, okay, and it asks for the acceleration, you got to take the derivative the first time and then a second derivative of s, okay? Which is the first derivative of v, okay? Alright, and somebody may ask, well, is there a third derivative? Yes, and the derivative of acceleration is called jerk. I want to say, it's kind of like when you're making sudden, you're coasting along, you make a sudden stop, you jerk a little bit. I don't know where it actually comes from, but that's one of the ideas, probably. Okay, so you know that the third derivative of acceleration, or the derivative of acceleration, is jerk. Yeah, that's just a trivial thing there. Okay, so when we come back, we're going to do one more of a first derivative. We're going to use related rates. Then we're going to look at the second derivative and when to use it. And probably just a couple of examples of the second derivative. After that, we'll get into integration and when to integrate. Okay, we'll get into one more first derivative and two examples of a second derivative, and then we'll get into integration type problems, and then I'm probably going to maybe review, I don't know if I will or not, but at least you'll have something here. And let me tell you something, you students who are taking AP Calculus this year, if you go to my YouTube video and if you subscribe, that's where you can get to it back easy. These first few lessons that I'm giving you are going to be very, very handy. It's not going to be the entire course, but at least you'll have an idea when to do what. And you don't want to be taking that test to figure out, well, what do I do here? Okay? Alright, so that's what I have here. I have some invaluable information that I can give you that will help you look at this and say, alright, if I go to KP the Math G's lesson on the Big 3 and AP Calculus, I'll learn when to use what. That's very valuable, and it saves a lot of time on the test. Whether it's a multiple choice test or whether it is a free response question. And believe me, guys, this will be the 206th YouTube video, so take advantage. It's AP Calculus alone, by the way. So take advantage of these opportunities and use them. You can always go to the search bar after you go to KP the Math G. Go to the search bar and say, maybe you want to learn a little bit about related rates. Well, every video that I've got will have something on related rates. And get this, a lot of them are going to come from a prior test. Isn't that something? So, a lot of good, valuable material here for your benefit. Alright, that's all I have for today. Getting ready to drive the bus. So, I'll be leaving in about 18 minutes from now. So, this is KP the Math G signing off. Ladies and gentlemen, if you need to subscribe, please do so. I usually say, oh, it doesn't matter if you subscribe or not. It does matter, because if you subscribe, then you can easily come to this. Okay? Please subscribe if you would like to do that. Please make a comment if you would like to make a comment. And then if you would like to hit that like button, please do so with that as well. Anyway, ladies and gentlemen, this is KP the Math G signing off. Have a great, great day. Signature clap. Okay.